1,000-ton stone block hangs in the air, silent and impossible. This is the enduring mystery of lost ancient engineering, where the past holds masteries we can scarcely explain. By the end of this journey, you will see human history in a completely new light, not as a straight line of progress, but as a story of towering achievements that were somehow forgotten. We will uncover how builders moved mountains, shaped granite like clay, and designed structures to dance with earthquakes. How did they accomplish feats that challenge our own modern tools? What does their forgotten wisdom say about our potential today? What forgotten chapter of human ingenuity are we only now beginning to read? The granite surface feels cool and impossibly smooth, a testament to a precision that defies its own age. This is the first cornerstone of our mystery, the megalithic enigma of stone cutting. Across the ancient world, from the pyramids to the high plains of Bolivia, we find stones weighing dozens of tons fitted together with joints so flawless that not even the thinnest blade of a modern razor can find purchase. This is not rough construction. This is machining on a monumental scale. Look at the andesite blocks of Puma Punku, carved with geometric precision and interlocking channels that look like components from some colossal, unknown machine. Or consider the granite boxes within the Serapeum of Saqqara in Egypt. These are not simple sarcophagi. They are immense containers, some weighing over 70 tons, carved from a single piece of rose granite. Their surfaces are flat to within a few thousandths of an inch, and their internal corners are sharp, complex, and perfectly square. Creating such a form today would require diamond-tipped tools, computer-guided milling machines, and a profound understanding of material stress. Yet these boxes were crafted millennia ago. How? The traditional explanation of copper chisels and stone hammers simply cannot account for the evidence to brute force, but to a profound, lost nuance in the art of movement. Some researchers, listening to indigenous oral histories and looking at peculiar evidence, wonder if sound played a role. There are traditions from various cultures that speak of stones becoming weightless when certain chants or frequencies were applied. While it sounds like myth, the principle is rooted in physics. Vibrational energy can dramatically reduce static friction, making a seemingly immovable object far easier to slide. It is a tantalizing idea that the first step in moving a megalith was not a push, but a resonant hum that changed its relationship with the earth. Look to Easter Island for a more tangible, yet equally brilliant method. The island's famous Moai statues, some weighing over 80 tons, were transported miles across rough terrain. For decades, the prevailing theory involved log rollers and large teams. But recent experimental archaeology, led by researchers like Carl Lipo, demonstrated a far more elegant solution. By using ropes to rock the statue side to side in a controlled walking motion, a small team could create forward momentum. This method transformed dead weight into rhythmic, manageable kinetic energy. It was not about dragging a burden, but about coaxing it into a dance. This reveals the collective intelligence behind these projects. It was not mindless toil. It was coordinated rhythm, a shared understanding of physics, and likely the cadence of work songs that kept hundreds of people moving in perfect, pulsing unison. Imagine the scene not as chaotic straining, but as a synchronized performance of human and stone. The organizational skill required to plan routes, build temporary causeways, manage food and water for the workforce, and execute the move without modern tools or communication is a staggering feat of project management. It speaks of societies that could think in decades, not just seasons, and mobilize their entire cultural energy toward a single, awe-inspiring goal. They mastered the horizontal plane, moving giants across the landscape. But then comes the final vertical challenge. Once the stone arrives at the sacred site, how do you lift it? This introduces a principle so simple yet so powerful it would define construction for millennia, the secret of the counterweight. The lever is a humble tool, but in the hands of a master, it becomes a whisper that moves the world. This is the third forgotten technique, the ingenious application of counterweights and levers, where ancient builders turned simple physics into a silent, monumental force. Imagine the final challenge, a lintel stone weighing as much as several elephants, now resting at the base of a stone circle. The vertical journey seems impossible. But then a timber frame is erected, ropes are woven from plant fibers, and the most crucial element is prepared, a basket or container filled with sand, acting as a counterweight. The principle is elegant. By attaching the counterweight to one end of a lever system and the massive stone to the other, a small team pulling on ropes could, over many careful cycles, raise the block inch by deliberate inch. The sand is key because it can be released slowly to control the descent of the counterweight, providing a smooth, manageable lifting force. This is not brute strength. This is controlled exchange, a dialogue between weight and counterweight. The construction of the Great Pyramid's inner chambers offers a stunning possible application. High within the pyramid's core are the massive granite beams of the king's chamber, each weighing over 50 tons. How were they lifted to such a height? The theory proposed by architect Jean-Pierre Houdin is compelling. He suggests the builders used an internal ramp, a corkscrew corridor built within the pyramid's own body. A sled bearing a granite block could be pulled up this ramp, but the real genius may have been in using the descending empty sled, or a dedicated counterweight system, to help haul the next loaded sled upwards. The pyramid itself, its immense mass and structure, became part of the lifting machine. This reveals a profound intuitive grasp of statics and dynamics. They understood that equilibrium was a state to be manipulated. They could calculate, likely through experience and geometric rules passed down through generations, the precise fulcrum points and counterweight masses needed to achieve stability. There are even hints in some ancient texts and reliefs of using water as a perfect, fluid counterweight in lock systems, a method that would require an advanced understanding of hydraulics and volume. This mastery of balance, of making one force perfectly oppose another, speaks to a mindset that saw the natural world as a set of interconnected energies to be harnessed. They didn't fight gravity, they negotiated with it using its own rules to achieve their aims, but placing a 1,000-ton stone atop a pillar is only half the victory. The true test comes when the earth itself begins to tremble. How do you ensure your masterpiece doesn't come crashing down? This leads us to the fourth, and perhaps most subtle, ancient mastery, the art of building structures that could dance with an earthquake. The ground shakes, but the walls do not fall. This is the fourth profound technique, seismic resilience through advanced foundation engineering. In regions where the earth regularly trembles, ancient builders created monuments that have outlasted empires by learning to dance with the quakes, not resist them. Look at the Inca walls of Cusco or the fortress of Sacsayhuaman in Peru. The stones are massive, irregular polygons that fit together in a breathtaking, interlocking puzzle. There is no mortar. The joints are so precise that you cannot slip a piece of paper between them. This is not just artistic skill. It is brilliant engineering. During an earthquake, a rigid wall of uniform blocks will crack along its straight lines of weakness, but a wall of interlocking, irregular stones has no straight lines to fail. Instead, the entire structure flexes as a single, living unit. The stones shift and settle slightly against one another, dissipating the seismic energy through friction and movement, then settle back into place when the tremor passes. It is engineered chaos, a calculated flexibility built into seemingly immovable rock. Across the world in Japan, ancient builders of pagodas employed a different but equally clever principle. These tall, slender towers have survived violent earthquakes for over 1,000 years. Their secret lies in a central pillar, a massive timber column that runs up the core of the structure but is not rigidly attached to the floors. It acts like a giant, suspended pendulum. When the ground shakes, the floors sway around this stable central axis, absorbing and neutralizing the energy. This is an early form of harmonic damping, a concept modern engineers use in skyscrapers today. The builders understood something fundamental, that to survive a dynamic force, you must allow for controlled movement. This wisdom extended even below ground. Evidence suggests some ancient cultures, including the Romans, used layered foundations. They would place structures on beds of gravel or sand, or even suspected materials like lead sheets. These layers act as shock absorbers, isolating the building from the worst of the ground's movement, a principle known today as base isolation. Where did this knowledge come from? It likely began with observing nature, watching how tall, flexible trees sway in a storm without breaking, or how loose soil absorbs an impact better than solid rock. They translated these natural lessons into stone and timber. This resilience speaks to a long-term vision we often struggle to grasp today. They were not building for a decade or a century. They were building for eternity, and they engineered their creations to converse with the very forces that could destroy them. It was a partnership with the planet's power. And if the foundation was aligned with the Earth's rhythms, the monument itself was often aligned with something far grander, the cosmos itself. The stones do more than just stand, they speak the language of the cosmos. This is the fifth profound technique, the seamless fusion of celestial alignment and monumental engineering known as archaeoastronomy. For these ancient builders, a temple was not merely a building. It was a permanent observatory, a calendar carved in stone, and a direct bridge to the heavens. Picture the dawn of the summer solstice at a place like Newgrange in Ireland. For just a few minutes, as the sun crests the horizon, a slender beam of light travels down a long, narrow passageway to illuminate a deep inner chamber, a tomb that has rested in darkness all year. This is not an accident. It is a feat of precision that required generations of meticulous sky watching and the monumental will to translate that knowledge into a landscape of rock and earth. The builders were master astronomers using simple but profound tools. A gnomon, a vertical stake in the ground, would cast a shadow whose changing length and direction over the seasons mapped the sun's journey. By marking the extremes of these shadows at the solstices, they could establish fixed, true north-south and east-west lines, the very axes upon which their sacred geometry would be built. They plotted sighting lines across miles of terrain, from one mountain notch to another, creating a giant, natural observatory to track the risings and settings of key stars. This long-term observation was a cultural project, a sacred duty passed from one generation of sky watchers to the next. The knowledge was then encoded with breathtaking ambition. At the Temple of Karnak in Egypt, the axis of the entire complex is aligned so that on the winter solstice, the setting sun would shine directly down the main avenue of sphinxes and through the innermost sanctuary. At Chichen Itza during the equinoxes, the play of light and shadow on the steps of El Castillo creates the illusion of a serpent slithering down the pyramid, connecting the sky god with the earth. And of course, at Stonehenge, the heel stone marks the sunrise on the summer solstice, framing it within the great trilithons. This celestial choreography served profound purposes. It created a reliable, immovable calendar for agriculture and ceremony, anchoring human life to the cosmic cycle. It demonstrated a mastery over the natural order, showing that the community understood and could even predict the motions of the gods themselves. The architecture became a statement of cosmic harmony, a permanent proof that human society was in alignment with the universe. The precision is so great that modern researchers can even use slight deviations in alignments to date the sites. Because the positions of stars shift very slowly over millennia in a process called the precession of the equinoxes, an alignment that is off by a tiny fraction today would have been perfect when it was built, giving us a celestial timestamp. This reveals a mindset that saw no separation between the spiritual and the scientific, between the act of building and the act of understanding the universe. They engineered not just with stone but with starlight, and this celestial order did not stop at alignments. It was woven into the very fabric of their designs through a sacred and universal language of shape and ratio. The blueprint was a prayer written in angles and ratios. This is the sixth profound technique, the mastery of sacred geometry and encoded proportion, where mathematics became the language of the divine and the secret to structural perfection. Walk through the ruins of the Parthenon in Athens, and you are not just seeing columns and steps, you are walking through a three-dimensional equation. The spacing of the columns, the curve of the stylobate, the height of the pediment, all relate to one another through the golden ratio, a proportion of roughly 1 to 1.618 that appears throughout nature, from the spiral of a nautilus shell to the arrangement of leaves on a stem. The builders did not use this ratio because it was merely pleasing to the eye. They believed it captured the very essence of harmonious growth, the fundamental pattern of a balanced universe. By embedding it into their architecture, they were aligning human creation with cosmic order, making the temple a point of resonance between earth and heaven. This principle echoes across continents. In Egypt, the dimensions of the king's chamber within the Great Pyramid are based on a 2-by-1 rectangle, and its diagonal relates to the mathematical value of pi. In India, Hindu temples are laid out as vast mandalas, geometric diagrams of the cosmos, with every courtyard, pillar, and spire positioned according to precise astronomical and symbolic calculations. This was not arbitrary decoration. It was a deliberate, sophisticated application of a universal code. To execute these designs on the scale of a pyramid or a cathedral required an absolute command of measurement. This is where standardized units like the Egyptian royal cubit come into focus. This was not just a ruler, it was a cosmological constant, a length derived from the Earth's polar radius divided by a specific, meaningful number. Using such a unit meant that every builder on every site was working from the same divine blueprint. It allowed for flawless scalability, enabling a master architect in Thebes to design a temple that could be perfectly constructed 800 miles away in Abu Simbel, because the instructions were not in vague descriptions, but in sacred, reproducible numbers. This geometric coding often extended into the very experience of the space. Some chambers, like the so-called King's Chamber in the Great Pyramid, are built from specific types of stone in precise dimensions that create unique acoustic properties. The space can amplify certain frequencies or create standing waves, turning ritual chants into something immersive and physically palpable. The building itself was an instrument engineered to shape not just sight but sound and feeling. This represents one of the most elegant forms of knowledge transmission in history. In a world before printed books, how do you preserve complex mathematical and philosophical ideas for millennia? You carve them into the landscape. You build them so large, so permanent, and so perfectly proportioned that they cannot be ignored or easily erased. The structure becomes a living textbook, its lessons waiting to be decoded by anyone who learns to read the language of its lines. What deeper secrets of resonance, of energy, of universal structure are still waiting to be heard in the silent hum of these stones? To translate these perfect geometric visions from parchment to permanence, the ancients needed a material that could defy time itself, a substance that could flow like water and then harden into stone. This necessity leads us to the seventh and perhaps most mysterious ancient technique, the lost alchemy of self-healing concrete. The dome of the Roman Pantheon has watched empires rise and fall for 2,000 years, a silent testament to a forgotten art of permanence. This is the seventh profound technique, the lost alchemy of self-healing concrete. While our modern bridges and sidewalks crumble after mere decades, Roman harbors like Portus Cossonus still stand firm, their submerged concrete blocks growing stronger with each passing century. The secret was not a single ingredient, but a sophisticated chemical recipe perfected through generations of trial and error. Modern Portland cement is a brittle material, prone to cracking as water and salts seep in, expanding and corroding the internal steel reinforcement. Roman concrete was different by design. Its magic lay in a specific mixture of lime and a volcanic ash called pozzolana, sourced from regions like Pozzuoli. When combined with seawater, this mixture triggers a slow, long-term chemical reaction. Tiny, plate-like crystals of a mineral called aluminous tobamorite begin to grow within the matrix. These crystals are not a flaw, they are the concrete's immune system. When a microscopic crack forms, water seeps in and reacts with the unused lime and volcanic glass in the mixture, forming new crystalline material that literally glues the crack shut. The concrete does not just resist decay, it actively heals itself. This was not accidental. It was the result of meticulous, empirical science. Roman engineers understood that different projects required different recipes. For harbor walls constantly battered by salt water, they used a specific coarse aggregate and a precise mixing technique that created a more porous, reactive interior. For the Pantheon's dome, a lighter mixture incorporating pumice was used to reduce weight while maintaining strength. This knowledge was a closely guarded craft passed down within builders' guilds. The full understanding of why it worked was a mystery until very recently, when advanced scanning technology allowed scientists to see the nanostructure of these ancient samples. They found the self-healing crystals in abundance, a feature modern concrete utterly lacks. This represents a paradigm of thinking we have only just rediscovered, the idea of designing materials that work with their environment, not just withstand it. The Romans built a dialogue between stone and sea. How many other formulas for such resilient composites have vanished into the dust of fallen libraries? This mastery of transforming humble earth into eternal stone finds a parallel in another ancient domain, the mysterious and formidable science of metallurgy. A blade that never dulls and a pillar that never rusts speak of a dialogue with metal itself. This is the eighth profound technique, the lost mastery of metallurgy that produced materials defying time. In the heart of Delhi stands the Iron Pillar, a 7-ton testament forged in the 4th century. It has endured 1,600 monsoons, countless cycles of heat and humidity, and yet it bears no significant rust. This is not a fluke of dry air, but a feat of forgotten chemistry. Modern analysis shows the iron possesses an unusually high phosphorus content and a low sulfur content, a specific recipe that, when exposed to the atmosphere over time, encourages the formation of a thin, protective film called mesawite. This film acts as a permanent, self-renewing barrier against corrosion. Did the Smiths understand the atomic reaction they were engineering? Perhaps not in our terms, but they understood the result, a ritualized recipe perfected over generations that yielded iron which could greet the centuries unchanged. This chemical intuition reaches its zenith in the legendary blades of Damascus steel. These were not ordinary swords. They were recognizable by a mesmerizing, watery pattern on their surface, a fingerprint of their incredible internal structure. The steel, known as woots, originated from India and was produced in small clay crucibles. The process was a closely guarded secret, involving specific iron ores with trace elements like vanadium, and a precise cycle of heating and slow cooling that allowed carbon to form in unique ways. When the ingot was forged, the smith would fold and hammer it repeatedly, not just to shape it but to align these internal structures. The result was a blade of legendary sharpness, flexibility, and strength, said to be capable of slicing a silk scarf floating in the air. The mystery deepened with modern science. When samples were examined under electron microscopes, researchers found carbon nanotubes within the steel's matrix. These microscopic structures, only identified in the late 20th century, would have contributed to the metal's phenomenal properties. This means the ancient smiths, through fire, hammer, and an unwritten science, were manipulating matter at the nanoscale. Their mastery was so complete that when the specific ore sources were depleted or the master-apprentice chains were broken, the full technique vanished, remaining superior to European steels for nearly 1,000 years. This deep manipulation of matter, this alchemical transformation of raw earth into supernatural material, leads to a final, tantalizing question. If they could converse with metal, could they have learned to speak to stone in a similar way? Across many ancient cultures from Egypt to South America, there are persistent legends and even some curious archaeological hints about plant-based concoctions, acids derived from herbs that could soften granite to a clay-like consistency, allowing it to be molded and shaped. While mainstream science remains skeptical, the notion is a powerful metaphor for the overarching theme of these lost techniques. It represents the ultimate ambition of these forgotten engineers, not to conquer nature with brute force, but to understand its deepest secrets so intimately that they could persuade stone to flow and metal to remember, turning the very substance of the world into a partner in creation. Their legacy is not just in the monuments that stand, but in the haunting possibility that they once held keys to material science that we are still, to this day, struggling to rediscover. The line between legend and lost science is etched into stone itself. This ninth technique, the enigma of stone softening and plant extracts, ventures into the most controversial and fascinating territory of all. Persistent stories from the Andes to ancient Egypt speak of a liquid derived from specific plants that could turn granite or limestone soft, almost like clay, allowing it to be molded or carved with ease before it re-hardened into its original stony strength. While mainstream archaeology often dismisses this for lack of definitive proof, the idea refuses to fade, suggesting a profound, forgotten dialogue between botany and engineering. Proponents of the theory look to certain anomalies. There are stones at sites like Sacsayhuamon or Ollantaytambo with surfaces that appear sculpted or molded, bearing flowing, organic curves that seem difficult to achieve with pounding stone hammers. Some tool marks resemble what might be left by a tool pressing into a pliable material, not chipping a brittle one. Early Spanish chroniclers in the Americas recorded indigenous tales of a plant whose juice could soften rock, accounts often written off as fanciful but recorded with surprising consistency. The scientific question at the heart of this is compelling. Could certain organic acids, perhaps from plants like the saxifraga or other species with high oxalic acid content, significantly weaken the silicate bonds on the very surface of a stone? Could an enzymatic brew, a product of deep ecological knowledge, act as a powerful chelating agent, temporarily making the rock more malleable? If such a process existed, even in a limited form, it would represent a breathtaking form of biochemical engineering, turning a living forest into a construction workshop. It suggests a worldview where nature was not an obstacle to be conquered, but a toolkit to be understood. Even if the literal idea of rock turning to soft clay is more metaphor than reality, the core concept holds a powerful truth. Ancient builders were masterful chemists of their environment. They almost certainly used natural acids from fruits like lemons or sour grapes as polishing agents, or plant-based oils as lubricants for drilling and cutting, reducing friction and extending the life of their tools. This pursuit of a fluid interaction with materials presents a stunning contrast to the solid, interlocking genius of polygonal masonry. One technique is about supreme rigidity and friction, the other hints at a temporary suspension of those very properties. It asks us to expand our imagination about what ancient technology encompassed. Their mastery may have been as much about the chemistry of plants and the patience of biological processes as it was about levers and geometry. This fluidity in thought, this willingness to see potential in every leaf and vine, might be the most important technique we have yet to fully appreciate. It points to a holistic science now silent that viewed the entire natural world as a partner in creation. A wall of 1,000 unique stones fits together like a single, unbreakable skin. This 10th technique, the structural genius of polygonal masonry, represents the absolute zenith of empirical stonemasonry. Look at the cyclopean walls of Mycenae in Greece or the foundations of Cusco in Peru. These are not piles of rock, they are intricate three-dimensional puzzles carved on a titanic scale, where each block is an irregular polygon, its neighbor's custom shaped to fit its every contour with breathtaking intimacy. There is no mortar, the bond is pure geometry and friction. The process to create such a wall was a monumental exercise in spatial reasoning. For each new stone, the masons would first carefully measure the gap in the existing wall. They might use a plumb line and a simple measuring rod to map the negative space. Then, at the quarry or on site, they would begin shaping a new block, not to a standard size, but to this specific, complex mold. This likely involved a patient dance of trial and error, chiseling, test fitting, marking high spots, and carving again. Some researchers suggest the use of wooden templates or even a system involving a master stone, a perfectly shaped block used as a reference to guide the carving of the stones meant to surround it. The true mastery, however, was not in the carving alone, but in the vision. The builder had to see the final, interlocked wall in their mind's eye before a single stone was cut. They understood topology, the way shapes relate in space, on an intuitive, practical level that modern engineers would need computers to simulate. The payoff for this immense labor was a structure of almost supernatural resilience. Unlike a wall of uniform bricks in a grid which has straight, weak mortar lines, a polygonal wall has no straight lines of failure. When force is applied, whether from an earthquake or a siege engine, that force is dissipated across thousands of angled contact points. Each stone presses against its neighbors, transferring load in a web of mutual support. The wall flexes as a living entity, settles and holds. It is a lesson in distributed strength, where the whole becomes infinitely greater than the sum of its parts. This method was not fast. It demanded generations of skilled artisans and a societal willingness to invest decades, even centuries, in a single project. Its eventual decline in favor of quicker, mortared brickwork speaks to a shift in priorities, perhaps towards rapid expansion or different aesthetic ideals. But its legacy is a stone-cold lesson in patience. It proves that when the goal is eternity, there is no substitute for perfect fit. This profound understanding of how shape dictates strength, of how to make separate pieces act as one, finds a strange and ethereal echo in the next realm of lost knowledge. If perfect physical alignment could create indestructible walls, could perfect sonic alignment achieve something even more miraculous, the gentle defiance of gravity itself. Sound itself becomes a tool, a physical force humming in the air. This 11th mystery, the accounts of acoustic levitation and resonance, asks us to listen to the oldest stories in a new way. From the high plateaus of Tibet to the deserts of Egypt, ancient texts and oral traditions speak of a profound secret. They tell of monks or priests using deep chants, the vibration of drums, or the precise note from a long trumpet to make massive stones lose their weight, to float into place as if guided by an invisible hand. To modern ears, this sounds like pure mythology, a symbolic tale of spiritual power. Yet, something in the persistence of these stories across unconnected cultures gives even skeptical researchers pause. It points to a universal human intuition that sound is not just something we hear, but something that can physically interact with the world. The scientific principle at play is resonance, the phenomenon where every object has a natural frequency at which it prefers to vibrate. Strike a tuning fork and a nearby fork of the same pitch will begin to sing in sympathy. Apply the right resonant frequency to a structure with enough energy, and you can induce dramatic vibrations, as soldiers breaking step on a bridge learned the hard way. The legendary technique, then, would involve discovering the precise sonic key for a specific stone, a frequency that would cause its crystalline structure to vibrate in perfect unison, potentially reducing internal friction and making it far easier to move. While we have no evidence of levitating megaliths, modern physics offers a fascinating parallel. Scientists today use ultrasonic standing waves, carefully calibrated frequencies of sound beyond human hearing, to levitate tiny droplets of water or small particles in mid-air. The sound waves create pockets of high and low pressure that can trap and suspend an object. It is a laboratory trick, but it proves a fundamental point. Sound can indeed counteract gravity on a small scale. This begs a tantalizing question: could a scaled-up, lost understanding of harmonic resonance, using massive drums or choruses of voices, have produced a similar macro-scale effect? The idea moves from pure speculation when we listen to the ancient sites themselves. Many temples, from the oracle chamber at Hypogeum in Malta to the Mayan pyramid of Kukulkan, possess extraordinary acoustic properties. Certain spots amplify whispers to be heard across a room, or create eerie echoes that transform a chant into an overwhelming, immersive experience. The builders clearly understood acoustics as an architectural element, designing spaces where sound behaved in specific, powerful ways. This was likely for ritual purposes to create awe and a sense of divine presence. But could that precise control of sound waves have also had a practical, engineering application? The line between the sacred and the scientific may not have existed for them. A ritual chant that aligned the community's spirit might also have been the precise cadence that helped coordinate the pull on ropes, or perhaps, in ways we do not yet understand, altered the physical task itself. These stories ultimately highlight a perception we have largely lost: that sound was a tangible, potent force to be harnessed, as real as a lever or a ramp. It suggests a technology not of gears and steel, but of vibration and harmony, where the mastery of invisible energy was considered the highest form of engineering. This seamless fusion of the practical and the ceremonial finds its most life-giving expression in the next great system, where engineering did not confront nature, but learned to converse with its most essential element. Water flows not as a servant but as a measured and willing partner. This 12th technique, the mastery of hydraulic engineering and water management, reveals a civilization's true ambition, its command over the very element that gives and takes life. In the baked streets of Mohenjo-Daro in the Indus Valley, over 4,000 years ago, one finds not just homes but a city built around a hidden circulatory system. Every house had a bathing area and a drainage outlet. Clay pipes carried wastewater into covered brick sewers that ran beneath the main avenues, complete with manholes for maintenance. This was not an afterthought. It was a foundational principle of urban design, a recognition that a city's health depended on its ability to manage flow, both clean and used. This understanding reached staggering scales in the Roman Empire. Their aqueducts are marvels of patient, precise surveying. To bring water from a distant spring into a city, engineers had to map a route dozens of miles long with a gradient so consistent, so gentle, that the water would neither stagnate nor erode the channel. They used simple but brilliant tools like the chorobates, a long, water-leveled table, to ensure this perfect slope across forests and hillsides. When they met a valley, they did not divert. They built soaring arches, turning necessity into monumental art. For deeper depressions, they engineered inverted siphons, leading the water down into lead pipes and back up the other side, harnessing pressure in a controlled, daring dance. This was applied physics of the highest order, all calculated in the mind and tested in the field without a single calculator. But perhaps the most elegant solution came from the arid landscapes of ancient Persia with the Qanat. This was a technology of profound humility and intelligence. Instead of chasing surface water, builders located a water-bearing layer in the foothills. They then dug a vertical shaft down to it. From there, they began tunneling a gently sloping underground channel back toward their settlement, digging new vertical shafts every 100 feet or so for ventilation and soil removal. The tunnel, always sloping just less than the natural water table, would gravity feed the water to the surface miles away, creating a cool, reliable oasis in the desert. It was sustainable, preventing evaporation, and it required no pumps, only an intimate knowledge of the hidden geography of water. These systems served a grand, holistic vision. Water was not just for drinking, it fed public baths that were centers of social life. It flushed away waste, preventing illness. It turned barren fields into gardens through irrigation channels. It even powered the earliest water mills for grinding grain. This represents a long-term pact with the environment. They did not merely extract a resource, they entered into a relationship with the hydrological cycle, guiding water from source to city to field with reverence and precision. In an age facing its own water crises, their principles of gravity fed distribution, sustainable tapping of aquifers, and the integration of water management into the very bones of a city are not relics but urgent reminders. They manipulated rivers and springs with a gentle, guiding hand. But what happens when the ambition grows even larger, when the goal is not to guide a landscape, but to invent an entirely new one? This leads to the ultimate expression of territorial command, the creation of artificial mountains. A mountain does not resist, it is reshaped into a staircase for the sky. This 13th technique, the monumental art of terracing and landscape sculpting, reveals a civilization's ultimate ambition to enter into a creative dialogue with the very bones of the earth. Look at the Ifugao rice terraces of the Philippines, often called the eighth wonder of the ancient world. Carved into the steep slopes of the Cordillera Mountains over 2,000 years ago, they are not merely fields. They are a vast, living architecture of stone and mud walls that climb thousands of feet, following the precise contours of the mountainside. Each level is a perfectly flat basin, engineered to hold water at a consistent depth. This is a three-dimensional puzzle of soil mechanics, hydrology, and community will. The builders had to understand how to create retaining walls that could withstand the immense pressure of saturated earth, using stones fitted without mortar, their own weight and clever shaping locking them into place. They engineered a capillary network of irrigation channels, diverting water from forested mountaintops and distributing it with gravitational precision to every single terrace from the highest to the lowest. This transformed an erosion-prone, unusable slope into a sustainable, food-producing landscape of breathtaking beauty and stability. It was the invention of new, fertile ground where none existed before. This same principle, elevating function into sacred form, reaches its zenith at places like Teotihuacan in Mexico. The Pyramid of the Sun is not just a pile of rubble and earth. Its core is a carefully engineered, stepped mountain. The terracing here serves multiple genius purposes. Structurally, the stepped layers act as massive retaining walls, distributing the colossal weight of the pyramid and preventing its core from collapsing outward. Ceremonially, each terrace creates a stage for ritual, a pathway for processions that mimic the ascent of a sacred peak. The entire structure becomes a recreation of a natural mountain, but one perfected by human hands, symbolizing the ordering of chaos into an axis of spiritual power. The builders were thinking in 4 dimensions. They planned for the flow of water during torrential rains, designing concealed drains within the structure. They anticipated the compaction of Earth over centuries. They orchestrated the movement of thousands of people during festivals across its vast surfaces. This required a form of large-scale modeling, a mental simulation of hydrological and geotechnical forces that would challenge modern engineers even with computers. How did they do it? Through generations of accumulated, intimate observation. They learned which soil mixtures compacted best, which slopes invited landslides, and how water seeks its own level. They turned this hard-won knowledge into a living, productive, and enduring monument. This mastery of shaping the surface world, of making the land itself an architectural medium, finds a profound mirror in its opposite endeavor. If they could sculpt mountains into habitable steppes, they could also delve deep into the Earth's heart, mastering the dark and dangerous art of tunneling through solid rock. The world above is mirrored by a hidden world below. This 14th technique, the fearless mastery of subterranean tunneling and mine engineering, reveals a civilization's willingness to venture into the very heart of the Earth. Deep in the Timna Valley, you can descend into hand-carved Copper Age mines, narrow passages where workers toiled by flickering lamplight over 5,000 years ago. This was not a haphazard digging. It was a calculated, dangerous, and brilliantly orchestrated operation. To extract the precious copper ore, miners employed a method called fire setting. They would build a hot fire directly against the rock face, heating it for hours. Then they would douse the glowing stone with water or vinegar, causing a violent thermal shock that cracked and weakened it, making it possible to pry away with stone hammers and bronze picks. It was a primitive form of blasting, requiring precise timing and a brave acceptance of the scorching heat and choking smoke that filled the confined space. Surviving in that environment demanded engineering solutions for the most basic human needs, primarily air. The miners developed sophisticated ventilation systems. They would dig 2 shafts down to the working level, often spaced apart. The difference in air temperature and pressure between the shafts would create a natural draft, pulling fresh air down one and expelling foul air up the other, a passive system that breathed life into the deep galleries. Equally critical was preventing collapse. They became experts in timber shoring, using wooden beams to create supportive frames that held the weight of the world above them. They learned to read the rock, identifying stable strata and avoiding fault lines, a practical geology born from observation and hard experience. The scale of some of these ancient mines is staggering, indicating an industrial operation. At sites like the Great Orme in Wales, tunnels stretch for miles. The logistics are mind-boggling. How did they remove tons of ore and waste rock from such depths? How did they provide light, water, and food for the workers? The evidence suggests organized teams, perhaps working in shifts, with baskets and ropes hauling material to the surface. This was a coordinated, large-scale effort, a testament to a society's ability to manage complex projects in the most hostile of environments. This deep earth confidence found its ultimate expression not in extraction, but in habitation. In the soft volcanic rock of Cappadocia, Turkey, entire cities were carved downward. Places like Derinkuyu are not simple caves. They are vast, multi-level subterranean metropolises, descending hundreds of feet and capable of sheltering thousands. They featured living quarters, stables, churches, wine presses, and communal kitchens. Engineers carved intricate ventilation shafts that reached all the way to the surface, providing fresh air to the deepest chambers. They dug deep wells to access groundwater. For defense, they fashioned massive, circular stone doors that could be rolled across key passageways, sealing the community safely inside. This was not a retreat, but a complete, planned adaptation of the underground world into a sustainable refuge. It represents a total reimagining of what a city could be, turning the Earth's protective bulk into architecture. What profound knowledge allowed them to do this? It was an intimate, generations-deep understanding of geology. They knew how to identify a stable, tough rock that could be carved yet remain strong. They could follow a seam of copper ore like a trail through stone. They possessed a mental map of the unseen, a confidence to shape the darkness into livable, functional space. This deep earth mastery, this comfort in the hidden realms, finds a perfect counterpoint in a discipline that looks not down but out across vast and open distances. If they could navigate and engineer the world beneath their feet with such precision, how did they apply that same sense of alignment and measurement to the world that stretched to the horizon? A straight line drawn across a map can connect wonders separated by continents. This 15th mystery, the puzzle of transcontinental alignments, asks if the ancient world was mapped by a hidden geometry. Enthusiasts point to what are often called ley lines, apparent alignments where sacred sites like the Great Pyramid, Stonehenge, and temples in Greece or Peru seem to fall along great circles or specific geometric patterns across the globe. Mainstream archaeology remains deeply skeptical, noting that with thousands of significant ancient sites, some random alignments are statistically inevitable. Yet the persistence of the idea invites a serious question about capability, not just coincidence. If any such grand design were intentional, what would it have required? It would imply a lost science of geodesy, the precise measurement of the Earth itself. To plot a true straight line over hundreds of miles, you must account for the planet's curvature. You would need a consistent unit of measurement, a way to maintain a true bearing across mountains and seas, and a motivation profound enough to coordinate efforts across generations and cultures. The practical methods for achieving such a feat, however, are within the realm of known ancient skill. Master surveyors could have used chains of mountain peaks as natural sighting markers, creating a series of intervisible points across a landscape. At night, they might have used the rising or setting of specific stars to establish a celestial bearing, a method accurate enough for long-distance navigation. Some propose the use of signal fires or reflective mirrors to communicate alignment over vast distances, a slow but possible way to correct course. The motivation for such an undertaking is perhaps the most fascinating part. If these alignments exist, they might not be a literal map, but a symbolic one, connecting sites of spiritual power into a web that mirrored celestial patterns or told a creation story across the land itself. It could have served as a guide for pilgrimage, a sacred geography that turned a journey into a walking prayer. Or it might reflect shared astronomical knowledge where different cultures, independently, built their most important temples where key stars appeared on the horizon, creating a pattern we now see from our satellite view. Whether born of deep design or meaningful chance, this concept stretches our understanding of ancient worldview. It suggests they may have perceived their planet not as a collection of separate territories, but as a single, interconnected organism, with veins of spiritual energy linking mountain to temple to spring. Their geographical thought operated on a heroic scale, thinking in continents and epochs. This grand vision of the world finds its perfect echo in the smallest detail of their craft, where that same demand for perfect alignment was executed not across miles, but across the hair's breadth gap between two fitted stones. The meeting of two wooden beams can be a conversation that lasts 1,000 years. This 16th mastery, the advanced art of woodworking and timber joinery, reveals an engineering tradition that chose flexibility and intelligence over brute mass. In stone-poor regions like Japan or the forested lands of northern Europe, ancient builders turned to the living material of trees, confronting a whole new set of challenges. Wood bends, it twists with humidity, and it decays. To build for eternity with it required not just carving, but a profound collaboration with its very nature. Look at the pagodas of Japan, which have swayed through countless earthquakes. Their resilience lies in the intricate lattice of joints, a system called kigyume. These are complex, interlocking connections carved with absolute precision, where tenons and mortises fit together like three-dimensional puzzles, entirely without nails or metal fasteners. During a tremor, these joints allow the structure to flex and absorb the energy, clicking and settling like the bones of a great wooden creature, then settling back into perfect alignment. It is architecture that breathes. This same principle of distributed strength through joinery reached towering heights in the medieval cathedrals of Europe. Here, master carpenters engineered vast truss systems for roofs that spanned incredible widths. These were geometric frameworks of timber, where each beam, brace, and tie was carefully sized and connected to transfer the roof's immense weight down to the supporting walls, creating open, awe-inspiring spaces below. The calculations for these loads and stresses were not written in equations, but in the embodied knowledge of the master carpenter, learned through a lifetime of apprenticeship and direct experience with how oak bears weight, how pine flexes, and how a well-cut joint shares a burden. This deep material knowledge extended to the open sea with the Viking longships. Their clinker-built hulls were formed from overlapping planks, riveted together. This created a hull that was not rigid but supple. In the punishing waves of the North Atlantic, the ship could twist and give with the water's force, a flexibility that made it incredibly strong and seaworthy. Each of these triumphs required an intimate, almost familial knowledge of different wood species. Builders knew which trees yielded timber best for compression, like the heartwood of oak for posts, and which were ideal for tension, like ash for bows or tool handles. They understood grain direction, cutting their pieces to work with the wood's natural strength. They mastered seasoning, drying timber slowly to prevent warping and cracking. And they developed ingenious preservation methods, treating wood with tar, lacquer, or chemical salts to repel insects and slow rot. This was a holistic craft where the selection of the tree in the forest was the first step in a decades-long process. The ability to take a material that grows and changes and shape it into a vessel that conquers oceans or a temple that defies quakes represents a complementary genius to the stoneworker's art. It is a testament to human adaptability, proving that mastery is not about the material you are given, but about the depth of your understanding of its soul. The fact that wooden structures from 1,000 years ago still stand today points silently to their final, critical secret, a hidden war against the inevitable forces of decay. A vibrant mural stares back at you across 40 centuries, its colors as fresh as the day they were painted. This 17th technique, the mastery of biocidal preservation and protective coatings, reveals an ancient war against time itself, fought not with stone but with chemistry. The artisans who decorated Egyptian tombs or carved intricate wooden panels knew their creations faced invisible enemies: sunlight, moisture, mold, and insects. Their response was a sophisticated arsenal of applied science. They did not simply paint, they engineered surfaces for eternity. The brilliant blues and greens on temple walls came from stable mineral pigments like azurite and malachite, carefully ground and bound with organic media, perhaps egg tempera or plant gums, creating a durable, cohesive film. Over this, they might apply a protective varnish made from tree resins like frankincense or myrrh, sealing the artwork from the air. For wood, the treatments were even more ingenious. Craftsmen in many cultures used hot plant oils or beeswax to penetrate the grain, creating a water-repellent barrier that also enhanced the wood's natural beauty. In the oxygen-poor environment of peat bogs, tannins from the bog water itself acted as a preservative, picketing wooden artifacts and even human remains in a state of remarkable preservation, a natural process ancient people likely observed and learned from. The fight against pests was equally clever. To protect precious textiles or wooden structures from insects, treatments involving salts, arsenic compounds, or the smoke from specific aromatic woods were employed. These substances acted as potent deterrents, a form of ancient pesticide born from deep environmental knowledge. Even the grandest structures received this proactive care. The Romans often coated their aqueducts and foundations with a mixture of lime and crushed pottery, called opus signinum, creating a hard, waterproof shell. Bitumen, a natural tar, was used in Mesopotamia as a sealant for baths and reservoirs. This was not mere maintenance. It was integral to the design, a final, calculated layer in a long-term preservation strategy. The famous self-healing Roman concrete, with its pozzolana ash, was itself a preservative marvel, chemically designed to resist the corrosive embrace of seawater. Each recipe, each treatment speaks of a profound intention. These builders and artists were not creating for the moment. They were in dialogue with the future, engineering a legacy meant to outlive languages and empires. Their coatings were a promise of permanence, a chemical covenant with time. Today, scientists study these ancient patinas, the thin layers on bronze statues that protect the metal beneath, or the specific compositions of pottery glazes that have remained intact for millennia, seeking clues for modern, sustainable preservation methods. What other defensive formulas lost to history once kept entire libraries safe from flame or rot? This defensive science, applied to protect beauty and knowledge, finds its most urgent and formidable expression when the threat is not slow decay, but immediate, violent destruction, in the ultimate engineering challenge of the fortress wall. A fortress is a machine for turning assault into futility. This 18th technique, the science of fortification and defensive architecture, represents ancient engineering under the most extreme pressure, where a single miscalculation could mean the end of a city. Look at the concentric castles of the Crusader era or the legendary Theodosian walls of Constantinople. These were not simple barriers. They were multi-layered systems of defense, each element a calculated response to a specific threat, blending physics, geometry, and a deep understanding of human psychology. The primary wall was just the beginning. Builders gave it staggering thickness, sometimes over 20 feet of solid masonry, to absorb the impact of battering rams and early projectiles. But height and thickness alone were not enough. The genius lay in the details designed to give every advantage to the defender. At the top of the walls, they built stone projections called machicolations, floors with holes through which defenders could drop stones, boiling liquids, or other deterrents directly onto attackers at the base, all while remaining protected. Below them, in the gatehouse ceiling, were murder holes, openings for the same harrowing purpose. The narrow, angled slits for archers were not just windows. They were carefully engineered, allowing a defender inside a wide field of view and firing arc, while presenting only a tiny, difficult target to an attacker outside. Even the gateway itself was a trap. Rather than a straight passage, architects designed bent entrances, forcing anyone who breached the outer portcullis to make a sharp turn, often under fire from above, before reaching the inner gate. This slowed the assault to a deadly crawl, breaking momentum and exposing the attackers from vulnerable angles. Beyond the stone, the very earth was shaped for defense. The glacis was a broad, steeply sloped earthen ramp built against the outer face of the wall. This made it nearly impossible for siege towers to roll close, and it forced attackers to charge uphill, exhausted under a hail of missiles. Later, when cannons arrived, the sloping face helped deflect shot and made the wall more resistant to mining attempts, as any tunnel would have to start much farther out. The placement of towers was a lesson in geometry. They were positioned so that their fields of fire overlapped, creating a deadly crossfire across every inch of the wall. Engineers calculated the dead zone, the area at the base of the wall that defenders could not see or shoot into, and designed outward projecting towers or wooden hoardings to eliminate it. This was systematic, iterative planning. How did they test these designs without computers? Through the brutal laboratory of conflict. each siege was a live test. Builders observed what worked where walls failed and how attackers innovated. The next fortress incorporated those hard-learned lessons, its design a silent record of the last war. This defensive ingenuity was universal. In the Andes, the Incas used their masterful polygonal masonry not just for temples, but for formidable sites like Sacsayhuaman. Those immense interlocking stones created sheer walls with no handholds, impossible to scale with ladders or grappling hooks. The irregular surfaces also deflected projectiles more effectively than flat walls. This was engineering for survival, a total mobilization of material knowledge and tactical foresight. It was all about redirecting and dissipating force, about making the energy of an attack work against itself. This same principle of mastering kinetic energy, of channeling force with precision, finds its opposite expression in the next great domain of lost engineering. If they could so brilliantly neutralize an enemy's power, how did they harness raw, elemental power for creation? The answer lies in the whisper of water and the groan of timber, in the forgotten world of ancient machines. A corroded bronze fragment holds a secret that rewrites history. Behold the Antikythera mechanism, recovered from a 2,000-year-old shipwreck off the coast of a Greek island. At first glance, it is just a lump of mineral-encrusted metal, but when researchers began to peer inside with modern X-ray technology, they saw something astonishing, a complex clockwork of at least 30 interlocking bronze gears. This was not a simple timekeeper. It was an intricate mechanical model of the cosmos, a portable device that could predict the positions of the sun, moon, and planets, forecast eclipses, and even track the cycle of the ancient Olympic Games. It has been called the world's first known analog computer, and its very existence shatters our timeline of technological progress. The technique behind it is a marvel of lost engineering. Each tiny gear had to be cast in bronze, then finished by hand with precisely angled teeth. These were not random cogs. Their tooth counts were specific mathematical ratios designed to replicate the irregular motions of celestial bodies as observed from Earth. Some gears even used a differential system, a complex arrangement that allows for the calculation of differences in rotation, a mechanism not seen again until the 19th century in modern automobiles. This implies a school of craftsmanship where metalworkers, astronomers, and mathematicians collaborated. They were translating abstract cosmic cycles into tangible, moving bronze. The knowledge required to design such a device represents a peak of Hellenistic mechanical genius that seems to vanish from the historical record after the 1st century BC. The Roman era, for all its civil engineering triumphs, showed little interest in such intricate philosophical machines, favoring practicality over cosmic modeling. The delicate art of precision gear cutting appears to have faded, its secrets perhaps kept within small, specialized workshops that were eventually lost to time, conflict, or simply a shift in cultural priorities. How many other such sophisticated devices once existed? Were there mechanical star charts in Alexandrian libraries or portable planetariums in the courts of ancient kings? Most would have been melted down for their metal or crumbled into unrecognizable dust. The Antikythera mechanism survives only by the accident of a shipwreck, preserved in the cold, dark silence of the seafloor. This single artifact forces us to completely reconsider the technological ceiling of antiquity. It proves that the ancient mind was capable of conceiving and constructing machines of breathtaking complexity, not with electronics, but with pure geometry and metallurgy made manifest. Their mastery of mechanics, it seems, may have extended beyond modeling the heavens to manipulating the very nature of sight itself, hinting at another forgotten craft, the art of shaping glass to bend light. Light itself could be bent and focused by a simple piece of shaped crystal. Among the treasures of ancient Assyria, now in the British Museum, sits a small, oval piece of rock crystal known as the Nimrud lens. Dated to around 700 BC, it is ground to a specific curvature, and while its purpose is debated, it is unmistakably a lens. It could magnify small objects, concentrate sunlight to a burning point, or correct for visual imperfections. Its very existence, quietly polished by an artisan 3,000 years ago, suggests a nascent but profound understanding of optics. The technique required to create it is deceptively simple yet demands immense skill. Starting with a rough piece of quartz or glass, the artisan would grind it against progressively finer abrasives, perhaps emery or sand, on a curved surface, patiently working it into a precise plano-convex shape. This was a marathon of patience, a dialogue between hand and stone to achieve a perfect curve that could gather and redirect light. While we have no surviving ancient telescopes, such a lens, paired with another, could form the basis of a simple spyglass. It invites a tantalizing question. Could this knowledge, hinted at in artifacts and legends, have allowed early astronomers to see a little further into the heavens? Could a polished lens have been the silent partner to those precise celestial alignments, offering a closer look at the wandering planets or the craters of the moon? The stories that surround this idea are powerful, like the legendary burning mirrors of Archimedes, said to have been arrays of polished shields used to focus sunlight and set invading Roman ships ablaze at Syracuse. Historians debate the practical feasibility of such a weapon on that scale, but the core concept is sound and demonstrates a clear grasp of optical principles. Whether used for starting fires, for the delicate engraving of seals and jewelry, for ceremonial magnification of sacred texts, or for early experiments in observation, these artifacts point to a forgotten chapter in the history of science. It reveals a culture that sought not just to observe light, but to command it, to turn a sunbeam into a tool and a piece of crystal into a window. This manipulation of light is the sibling to the mastery of its counterpart, heat, a duality that powered the most transformative craft of all, the alchemy of the furnace where sand became glass and ore became metal. The heart of a forge holds a conversation with fire that can last for days. This 20th technique, the mastery of high-temperature industrial kilns and forges, reveals a world where fire was not merely a tool, but a living element to be coaxed, contained, and commanded. To create the legendary steel of a Damascus blade or the silent, eternal ranks of the terracotta army, ancient artisans had to achieve and sustain heat that defies belief, often exceeding 1,200 degrees Celsius. This was not a matter of building a bigger bonfire. It was a sophisticated science of thermal engineering, born from generations of patient observation and daring experimentation. The furnace itself was the first masterpiece. Its shape was a careful calculation. Many were built with a tall stack, utilizing the chimney effect where hot air rising draws in a fresh, oxygen-rich draft from below, naturally stoking the flames to a fiercer intensity. For even greater control, they employed bellows, often made from animal skins, to force air directly into the heart of the fire. This precise control of oxygen was everything. In metallurgy, a reducing atmosphere, one with limited oxygen, was essential to pull impurities from iron ore and allow carbon to integrate, creating the first crude steel. In ceramics, the atmosphere determined color. An oxidizing fire, rich in oxygen, would turn clay a warm red, but seal the kiln to cut off oxygen, creating a reducing atmosphere, and the same clay could emerge with a deep, lustrous black. The artisans were essentially painting with air and flame. The materials they used to build these furnaces were just as critical. They lined the inner hearths with special refractory clays or crushed ceramics that could withstand repeated, searing heat without cracking or melting. For fuel, they mastered the production of charcoal, which burns far hotter and cleaner than raw wood, providing a consistent, controllable heat source. The scale of some ancient production sites speaks to an almost industrial level of organization. The kilns that fired the thousands of unique terracotta warriors were not backyard operations. They were part of a vast, standardized system, with different workshops specializing in heads, torsos, or limbs, all relying on identical firing techniques to ensure every figure, though individually crafted, possessed the same durable ceramic strength. How did they measure this inferno without a single thermometer? They learned to read the fire's language. The color of the flames, from a dull red to a blinding white heat, gave a visual gauge. The behavior of the fuel, the sound of the draft, even the way a test piece of clay or metal reacted when withdrawn, all provided feedback. It was an empirical, sensory science, a deep bodily knowledge passed from master to apprentice. This command over transformative heat was the engine of material progress. It allowed for the smelting of copper and tin to create bronze, the alloy that defined an age. It enabled the glazing of pottery, creating vessels that were both beautiful and impervious to water. And it laid the groundwork for the alchemy of pigments, where minerals and plants, subjected to precise heat, could yield vibrant, permanent colors like Egyptian blue or the rich reds of cinnabar. They had learned to build a tiny, temporary sun on Earth, a contained star whose breath could turn Earth into metal, clay into art, and sand into glass. This profound dialogue with elemental power finds a quieter but equally vital expression in the next realm. If they could command the fury of the forge, they also mastered the gentle, persistent art of coaxing life from the most stubborn ground through a forgotten science of the soil. A single drop of Tyrian purple dye was once worth more than its weight in gold. This 20-second mastery, the intricate chemistry of ancient pigments and dyes, reveals a world where color was not merely decorative, but a profound expression of wealth, power, and deep scientific understanding. To produce that legendary purple, artisans undertook a staggering industrial process. It began with harvesting thousands of a specific Mediterranean sea snail, the Murex brandaris. The snails were crushed, and their hypobranchial gland was extracted to yield a tiny amount of a yellowish liquid precursor. This liquid was then exposed to sunlight and air in a precise, days-long fermentation process, undergoing a complex photochemical reaction that transformed it through a spectrum of colors, finally settling into that deep, rich, and incredibly stable purple. The scale was immense, with ancient middens containing millions of crushed shells, a testament to an industry built on microscopic chemistry. This was not guesswork. It was a controlled, multi-step biochemical procedure, a recipe guarded as a state secret. The pursuit of blue was equally ambitious. True ultramarine, derived from the precious lapis lazuli stone mined only in Afghanistan, was ground and painstakingly purified through a water-based washing process that separated the brilliant blue particles from the gray rock matrix. But perhaps the most revolutionary was Egyptian blue, considered humanity's first synthetic pigment. Created over 4,000 years ago, it was made by heating a mixture of silica sand, copper carbonate, calcium carbonate, and a natron alkali to around 850 degrees Celsius. The result was calcium copper silicate, a stable, vibrant blue that could be ground into a powder for paint or shaped into objects. This required a precise understanding of raw materials, stoichiometry, and kiln temperatures, effectively creating a new compound through chemistry. For textiles, the science deepened with the use of mordants. These were metallic salts like alum or iron sulfate that acted as molecular bridges. A dye molecule might not bind directly to a fabric fiber, but a mordant would chemically bond to both, locking the color in place. Different mordants could also alter the final hue, turning the same plant dye, like madder root, into shades of red, orange, or even black. This knowledge of pH, solubility, and ionic bonding was applied science of the highest order, developed through centuries of experimentation. The proof of their success is in the artifacts themselves. While modern synthetic dyes often fade, these ancient colors, from the blues in Tutankhamun's tomb to the reds in Pompeian frescoes, remain radiant millennia later. Their formulations were engineered for eternity. This molecular mastery extended beyond sight to other senses. What ancient recipes for powerful adhesives, derived from tree saps and animal collagens, held stone and wood together? What complex herbal distillations served as medicines or perfumes, their exact botanical blends now forgotten? Each vibrant pigment is a fossilized idea, a permanent record of a chemical conversation between human ingenuity and the raw materials of the earth. This ability to transform the essence of a material, to extract a universe of meaning from a snail or a stone, represents a cognitive leap. It is the small-scale mirror of the grand landscape engineering we've seen, proving that their command over the physical world operated at every scale, from the continental to the microscopic. A single man moved over 1,000 tons of coral rock by himself. In the early 20th century, a Latvian immigrant named Edward Līdzkalnis began a solitary 28-year project in Florida, carving and constructing what he called coral castle from massive blocks of oolite coral, some weighing as much as 30 tons. He worked mostly at night, shrouding his efforts in secrecy, and when asked how he managed such feats alone, he would only say he had rediscovered the building secrets of the ancient pyramid builders. His tools, discovered after his passing, were astonishingly rudimentary, a collection of simple tripods, chains, blocks, and hand-cranked winches. No cranes, no hydraulics, no power tools. The mystery of Coral Castle is a modern echo of the ancient puzzles we have been exploring. It stands as a powerful testament that monumental construction does not necessarily require advanced technology as we define it today, but rather an intimate, almost poetic understanding of leverage, balance, and center of gravity. Līdzkalnis' genius seems to have been in the meticulous application of fundamental physics, using his simple tools in clever, compound ways. He likely employed a principle called the king's knot, a specific arrangement of ropes and pulleys that can create a mechanical advantage so great a child could lift an automobile. By using a tripod as a stable fulcrum and a chain as an infinitely flexible lever, he could have incrementally raised stones, pivoted them, and guided them into place with patient, solo effort. His story forces a crucial distinction in our search for lost techniques. It asks us to separate what is truly lost, like the chemical recipe for self-healing concrete or the nanoscale forging of Damascus steel, from what is merely forgotten or underappreciated, the profound results possible from the relentless, ingenious application of simple mechanics. Līdzkalnis was a modern individual innovator operating outside established engineering paradigms, much like the anonymous master masons of antiquity who first discovered how to make polygonal walls earthquake-proof. His castle is a monument to obsessive, practical intuition. It suggests that some ancient wonders may not stem from a single, grand, vanished technology, but from a culture-wide fluency in the silent language of weights and forces, a common knowledge so deeply embedded it required no explanation for its time. What simple secret did he grasp that we, in our age of computer-modeled stresses and powered machinery, have simply overcomplicated? Perhaps it is the forgotten art of listening to the stone, of feeling through the tools exactly when a multi-ton block is poised to pivot, and applying force not against it, but in concert with its own desire to move. This modern enigma brings our journey full circle, back to the most fundamental act, the very first step in all these endeavors. Before a stone can be moved, shaped, or lifted, it must be freed from the earth itself. This returns us to the primal question of quarrying, where the conversation with the mountain truly begins. The mountain itself was the first workshop, a vast canvas of living stone. Before any block could become part of a temple, it had to be persuaded to separate from the earth in one perfect piece. The ancient quarries at places like Aswan in Egypt or Baalbek in Lebanon are not just holes in the ground. They are immense open-air factories. Their very walls are testament to a sophisticated and patient science of extraction. This was not a matter of smashing rock. It was a careful dialogue with geology itself. The first step was reading the stone. Master quarrymen would walk the site, looking for natural fissures, assessing the grain of the granite or limestone, identifying the planes along which the rock would most willingly split. They were searching for the stone's own intention, its hidden lines of weakness. Once they found the perfect seam, they would begin a process of guided fracture. One of the most common and brilliant methods involved drilling a series of closely spaced holes along the intended separation line. These holes were not random. They were precise markers. Into these holes, dry wooden wedges were driven. Then, water was poured over the wedges. As the wood absorbed the water, it expanded with tremendous, gradual force. This slow, even pressure would coax a clean crack along the line of holes, parting the stone from the bedrock as neatly as slicing a loaf of bread. It was a technique of immense control, using the natural properties of wood and water to do the work of a giant's hand. For harder stones like granite, there is evidence of a more dramatic method, thermal shock. Workers might light fires directly against the rock face, heating it intensely, then suddenly douse it with water or perhaps vinegar. The rapid contraction would cause the surface to spall and flake away, weakening the stone for further work. This was risky, as it could introduce hidden cracks, but in skilled hands, it could efficiently shape the most stubborn materials. The organization within these quarries was a marvel of industrial logic. They were engineered landscapes. Builders carved level working platforms around the emerging block, creating space for teams to operate. They cut ramps and channels into the quarry floor, planning the exit route for a multi-ton stone before it was even fully freed. At Baalbek, the famous stone of the pregnant woman, weighing an estimated 1,000 tons, lies in its quarry, partially undercut and ready for transport, a snapshot of a process frozen in time. Most telling of all is the evidence of pre-shaping. Many blocks were not rough-hewn boulders hauled to the building site. They were meticulously dressed and shaped right there in the quarry. Excess stone was carved away, angles were defined, and even the beginnings of intricate joint work might be started. This served a dual purpose of genius. First, it dramatically reduced the weight for transport, a critical consideration when moving 100 tons of granite. Second, it meant the most labor-intensive carving, the noisy, dusty work of shaping, was done at the source, leaving the sacred temple site a place of precise assembly and quiet ceremony. This level of planning implies a master architect's vision was present from the very first cut. They had to sequence the extraction like a three-dimensional puzzle, knowing which block to remove first to access the next, all while maintaining the stability of the quarry walls for worker safety. It was a long-term project, a symphony of geology, physics, and logistics. Once a block was liberated, resting on its bed of prepared earth, the next challenge began. How do you move this geological newborn? The answer may involve a technology so familiar we overlook its ancient mystery, but in a form far removed from the simple cart. The wheel was known, but for moving megaliths, something more fundamental was needed, a principle of motion that reduced friction to almost nothing. The wheel was a celebrated invention, yet it is conspicuously absent from the scenes of our greatest ancient constructions. This is the 25th mystery, the limited use of the wheel in megalithic transport. We find elegant chariots buried with pharaohs and delicate potter's wheels spinning clay, but when it came to moving a 1,000-ton obelisk, the evidence points overwhelmingly to sledges, ropes, and rollers, not to carts. Why would cultures that understood the principle so well avoid its most obvious application for their grandest projects? The answer lies not in a lack of imagination, but in a profound pragmatism. Wheels are brilliant on paved roads and hard, flat ground. They transform friction into smooth rotation. But take that same wheel to the soft sand of a riverbank, the uneven bedrock of a quarry ramp, or the muddy earth after a rain, and it becomes a liability. It digs in, it bogs down, it requires an immense amount of energy just to overcome its own rut. A sledge, by contrast, presents a broad, flat surface. By wetting the sand or using a lubricant like animal fat on wooden rails, you create a consistent, low-friction interface that can be managed by large teams pulling in unison. The sledge adapts to the terrain. The wheel demands the terrain adapt to it. There is also the staggering issue of scale. Constructing a wooden wheel and axle strong enough to bear 80 tons without shattering is a major engineering feat in itself, requiring immense timber and master carpentry. Why invest that specialized labor when you have an abundance of human power and simple materials like logs, which can be used as rollers and then repurposed? Some societies may have simply found it more efficient to organize 1,000 people with ropes than to build and maintain a fleet of colossal, fragile carts. This leads to a fascinating hybrid idea, the rolling cradle or wooden sphere. Imagine not a solid wheel, but a set of large, sturdy wooden balls placed in a carved wooden track beneath a sledge. As the sledge is pulled forward, the spheres rotate within their channel, combining the easy rolling of a wheel with the stability and load distribution of a tracked system. It is an elegant, context-specific solution that leaves little archaeological trace as the wood would decay. This selective application reveals a core tenet of lost engineering philosophy. They were not technologists in our modern sense, chasing innovation for its own sake. They were solutionists, masters of appropriate technology. They asked not what was the most advanced tool available, but what was the most effective tool for this stone, on this soil, with these people. The wheel was not forgotten, it was simply reserved for the jobs it did best. Their genius was in matching the method to the moment, a flexibility of mind that built civilizations without being enslaved by a single invention. This pragmatic, almost ecological way of thinking extended to every facet of their work, suggesting their greatest tool was not made of wood or bronze, but was a way of seeing the world as a set of relationships to be balanced. A stone bridge stands not by crushing weight, but by a graceful conversation of forces. This is the 26th technique, the revolutionary mastery of arch and vault construction. Look at the soaring arc of a Roman aqueduct, striding across a valley as if the stone itself learned to defy gravity. Or stand beneath the immense dome of the Hagia Sophia, a vast sky of masonry floating overhead with no central pillar to hold it up. This was not merely a stylistic choice, it was a fundamental breakthrough in how to enclose space, a leap from the limitations of the post and lintel. The secret lies in a beautiful and counterintuitive principle, compression. In a true arch, each wedge-shaped stone, called a voussoir, is cut with absolute precision. When placed in sequence on a temporary wooden frame, these stones lean against one another. The final piece, the keystone, locks them all into a state of perfect, tense balance. Once the supporting frame is removed, the weight of the structure and anything above it is transformed. Instead of pushing straight down, the force travels sideways along the curve of the arch, transferred from stone to stone, until it is channeled vertically down into the massive supporting piers at either end. The entire structure becomes a continuous chain of mutual support, where every element is held in place by the pressure of its neighbors. It is architecture as a frozen moment of equilibrium. To achieve this, the stone cutting had to be flawless. Each contact surface between voussoirs needed to be perfectly angled so that the weight was distributed across the entire face, not just on a high point. A single poorly cut stone could create a point of failure, a crack that would propagate and bring the whole assembly down. The temporary wooden framework, the centering, was itself a feat of carpentry. a sacrificial skeleton that had to be strong enough to hold the entire weight of the unfinished arch until that magical moment when the keystone was tapped into place and the arch became self-supporting. The Romans, with their command of concrete, pushed this concept into 3 dimensions. They extended the arch into the barrel vault, a continuous arched ceiling, and then intersected vaults to create groined ceilings. Their ultimate triumph was the dome, a hemisphere that is essentially an arch rotated around its center. The Pantheon's dome, cast in concrete, is a perfect embodiment of this. Its thickness decreases as it rises, and its interior is coffered, both techniques to reduce weight without sacrificing strength. The oculus at the top, the open circle, is the final keystone, a ring of compression that completes the form. This innovation reshaped civilization. It allowed for vast public spaces like basilicas and bath complexes, where citizens could gather under a single, unifying roof. It created bridges that could span wide rivers with fewer piers, disrupting the flow less and lasting for millennia. It enabled monuments of overwhelming grandeur that spoke of a society's confidence and technical prowess. How did they first conceive of such an idea? Perhaps by observing natural arches in stone, or by noticing how a loose pile of bricks in a doorway could support itself if arranged just so. It represents a cognitive leap from seeing materials as passive loads to seeing force as a fluid that could be directed and shared. This profound understanding of directed force, of channeling immense power along a predetermined path, finds a stark and formidable parallel in another ancient discipline. The same principles that allowed a vault to gracefully bear a mountain's weight were applied to projectiles designed to break down walls in the relentless engineering of siege engines. The groan of a massive wooden arm under tension is the sound of physics weaponized. Engineering in ancient artillery and siege weapons represents a terrifyingly beautiful application of lost mechanical mastery, where the principles of the lever and the spring were scaled up to become engines of war. These were not the crude battering rams of popular imagination. They were precision instruments, the culmination of generations of trial and error in applied mechanics, designed to convert stored potential energy into devastating kinetic force with mathematical consistency. Consider the ballista, essentially a giant crossbow. Its power came not from a simple bow, but from 2 separate arms, each inserted into a vertical bundle of twisted animal sinew or hair. These skeins acted as torsion springs. When the arms were winched back, they twisted these bundles, storing immense rotational energy. Releasing the trigger unleashed that tension, snapping the arms forward to launch a heavy iron-tipped bolt with enough force to penetrate shield, armor, and soldier in a single horrific strike. The precision required was immense. The 2 torsion bundles had to be wound to exactly the same tension to ensure the projectile flew straight. The wooden arms had to be crafted from a single, flawless piece of resilient timber, shaped to flex without snapping. Every component, from the iron claw that gripped the bowstring to the ratchet mechanism of the winch, was a specialized piece of hardware. This craft reached a zenith in the Hellenistic period with machines like the repeating ballista attributed to Dionysius of Alexandria, a device that used a gravity-fed magazine to fire a rapid succession of bolts, an ancient precursor to the machine gun. But the ultimate expression of this martial physics was the trebuchet. This machine operated on a different principle, the counterweight. A massive pivoting beam had a sling on one end and a huge box of stones or earth on the other. When the counterweight was released, it fell in a steep arc, whipping the sling end around in a wide circle. The genius was in the sling itself, which acted as an extension of the lever, and its release mechanism, which timed the projectile's launch for maximum velocity and distance. A well-engineered trebuchet was a ballistic calculator made of wood and rope. Its operators could adjust range not by changing powder, but by adding or removing weight from the counterweight box, or by altering the length of the sling. Building these machines was a grand collaborative effort. The mathematician calculated the ideal leverage ratios and trajectories. The carpenter selected and shaped the timbers, understanding grain and strength. The metalworker forged the essential pins, hooks, and plates that held the immense stresses together. They were constructed from standardized parts where possible, so that a machine built in a workshop in Rome could be assembled by engineers on a frontier in Britain. Their effectiveness depended entirely on this reliability under the chaos of a siege. A machine that shattered on its first shot was worse than useless. It was a demoralizing waste of precious time and resources. How were they tested? Likely in dedicated proving grounds far from enemy eyes where different designs competed. Teams would have tracked the distance and impact of shot after shot, refining the designs through rigorous empirical data. This martial engineering, for all its destructive purpose, shares a profound common root with the most peaceful of ancient pursuits. The same need to measure force, calculate trajectories, and understand material limits was also the foundation of astronomy, architecture, and commerce. The mind that could plot the arc of a 90-pound stone to strike a castle wall at a precise point was using the same geometric reasoning that could plot the course of a planet across the night sky. It was all applied mathematics, a language of prediction and control. This relentless drive to quantify the world, to turn observation into reliable action, leads us to the silent infrastructure that made such grand projects possible, the unglamorous but vital mastery of managing the most fundamental resource of all, the labor and sustenance of thousands. A master builder in Memphis could send a blueprint to a quarry in Aswan, confident it would be understood. This 28th technique, the invisible framework of standardized measurement systems and metrology, was the silent language that made every grand collaboration possible. Without it, the pyramids would be piles of mismatched stone, and the Roman roads would wander into the wilderness. The establishment and enforcement of universal units was not a bureaucratic afterthought. It was the very first act of engineering, the agreement upon a common reality before a single block was cut. In Babylon, the consistency of brick dimensions across centuries of construction is astounding. Each brick was a modular piece of a vast, city-wide puzzle, and that puzzle only worked because every artisan, from the clay mixer to the bricklayer, was reading from the same measure. In Egypt, the royal cubit was more than a unit. It was a cosmological constant. Carved into black granite or inscribed on a wooden rod, this standard length, roughly 20.5 inches, was derived from the length of the pharaoh's forearm plus the width of his hand. But it was then fixed, removed from any individual's body, becoming an abstract, perfect ideal. Replicas of this cubit rod were distributed to workshops and sites across the kingdom. This meant that a column drum shaped in a quarry hundreds of miles up the Nile would fit perfectly into its waiting base at Karnak, because both were carved to the same invisible ruler. This allowed for a revolutionary division of labor. Work could be prefabricated, teams could specialize, one group cutting lintels to a specified cubit length, another shaping foundation blocks, all with the serene certainty that their work would converge into a coherent whole. The tools that translated these standards onto the land were marvels of simple genius. The groma, a cross of arms with hanging plumb bobs, allowed Roman surveyors to stake out perfect right angles for their military camps and city grids, creating order from chaos with a glance. The chorobates, a long, water-leveled table, ensured that aqueducts maintained their life-giving, gentle slope across miles of undulating terrain. These were the physical extensions of the standardized unit, the means to project a perfect geometric idea onto the imperfect earth. This systematization speaks of a civilization thinking at the scale of the state. It required administrators who could think in numbers, scribes who could record them, and a culture of trust in the abstraction of a measurement. But within these systems often lay a deeper, more beautiful secret. The ratios between units were frequently not random. The Egyptian system related the digit, the palm, the hand, and the cubit in harmonious proportions. These relationships created a built-in mathematics, a framework where design became an expression of number. When an architect planned a temple, he was not just counting cubits, he was weaving a pattern of sacred ratios into the very floor plan. The standard unit provided the consistent beat, and the ratios between units composed the melody. This mathematical order was the unseen grid upon which the visible glory of symmetry, ornament, and proportion was hung. The fluting on a column, the spacing of pillars, the height of a door, all could be calculated as multiples or fractions of the fundamental unit, creating a harmony that the eye feels even if the mind does not consciously count. The loss of a standard is the dissolution of a shared dream. When the cubit rods were lost or the guild knowledge faded, the ability to recreate the old precision faded with them. Their metrology was a covenant of cooperation, the agreement that allowed 1,000 hands to build as one. A carving on a temple wall is not merely decoration, it is a structural promise fulfilled. This 29th technique, the profound integration of art and engineering in ornamentation, reveals a world where beauty was not applied to a building, but born from its very bones. Walk through the corridors of Angkor Wat in Cambodia, and you are surrounded by a mountain of narrative. Every surface, from the grand bas-reliefs depicting epic battles to the delicate devotas gracing the pillars, was part of the original architectural plan. The builders did not construct a blank stone box and then invite sculptors in. From the moment the first foundation stone was laid, the sculptural program was already mapped in the minds of the master architects. This was achieved through brilliant logistical planning. They would leave blocks with raised, unfinished sections called boss stones. These protruding bumps of stone were not mistakes. They were intentional reserves of material, left by the masons so that master carvers could later transform them into divine faces, floral motifs, or intricate patterns without weakening the wall's core. The structure itself was designed as a canvas, with wall thicknesses calculated to accommodate the depth of future carvings, and load-bearing columns shaped with extra mass to be later fluted or carved into statues of gods and goddesses. This required a seamless, lifelong collaboration between the engineer and the artist. The engineer had to understand the stresses involved, knowing how much stone could be safely removed from a lintel or a pillar without compromising its strength. The artist had to grasp the principles of load and support, ensuring their chisel followed the stone's natural grain and respected the invisible lines of force holding the entire edifice together. Their communication was the silent language of the blueprint and the rough model, a shared vision that spanned decades. This fusion reaches its most breathtaking expression in the Gothic cathedrals of Europe. Here, the stone seems to defy its own nature. Soaring vaults are supported by flying buttresses that are themselves intricately carved. The famous rose windows are not just stained glass art, they are brilliant structural feats, acting as vast, radiant keystones that help distribute the weight of the surrounding stone. Most astonishing are the choir screens and the spires, where stone is carved into such delicate, lace-like tracery that it appears to be lace woven from rock. In these moments, the ornament does not adorn the structure, it is the structure. The aesthetic ambition drove the engineering innovation, pushing the limits of what was physically possible to create an experience of transcendent lightness and luminosity. The logistical coordination for such projects is almost beyond comprehension. It meant scheduling teams of quarrymen, layers, carvers, and glaziers in a complex, overlapping dance. The foundation layers worked ahead, while in the stoneyard, artisans pre-carved elements based on precise templates. A capital for a column might be largely finished on the ground, its design perfectly matching the architectural drawings before being hoisted into place high on the nave. This was not a linear process, it was a symphony of parallel creation. The result is a cultural potency that pure engineering alone could never achieve. The building becomes a sacred text in stone, its walls telling stories to an often illiterate populace, its very form evoking the heavens and inspiring devotion. This holistic vision, where a column could be both a necessary support and a teaching tool, where light was both a physical phenomenon and a metaphor for the divine, stands in quiet contrast to a more modern separation of disciplines. It suggests that for these master builders, truth was not found in mere function or mere form, but in their inseparable, glorious union. The master's hands moved and the apprentice's eyes followed. This is the 30th and perhaps most fragile mystery, the silent transmission of knowledge through generations. How does a society teach its children to build a cathedral that will take 200 years to complete, a project they will never see finished? The answer lies not in libraries but in the intimate, wordless space of the workshop. The master-apprentice system was the living library of ancient engineering, a vessel for what we now call tacit knowledge. This is the knowledge that cannot be written down, the intuitive feel for when a piece of iron is at the perfect cherry red heat for forging, the exact sound a chisel makes when it strikes granite at the correct angle, the subtle shift in weight that tells a team of rope pullers to pause and adjust. These were lessons taught by gesture, by correction, by shared silence over a task that took a decade to learn. A master mason did not give a young apprentice a textbook on compressive strength. He placed a mallet in his hand, guided his strike on a piece of practice stone, and said, "Again until it feels true." This education was a total immersion, a slow absorption of culture, ethics, and physics all at once. The apprentice lived with the master, ate at his table, and learned the craft's rituals alongside its techniques. The process built more than skill, it built a specific way of seeing the world. The guilds that grew around these trades formalized this transmission. They were not just unions, they were custodians of quality and mystery. To enter a stonemason's guild, one progressed from apprentice to journeyman, traveling to other workshops to learn variations on the craft, and finally, after producing a masterwork judged by his peers, to master. This system created a monopoly, yes, but it also enforced an unbroken chain of excellence. The secret to mixing a perfect lime mortar or tempering a sword blade was a guarded treasure, passed only to those who had proven their dedication and character. This made the knowledge profoundly vulnerable. A plague that swept through a city could wipe out an entire generation of master glassmakers. A war could scatter the guilds. A master could pass without a worthy successor, taking his most subtle secrets to his resting place. When the chain snapped, the loss was often permanent. We can analyze the chemical composition of Damascus steel, but we may never know the exact sequence of folds, the specific chant or rhythm of the hammer blows that the smith used to align the crystalline structure within the metal. We can measure the joints of an Inca wall, but can we ever truly inhabit the mindset of the mason who could look at two irregular stones and see, in his mind's eye, the single perfect shape that would make them lock together? That intuitive leap, that moment of creative geometry, died with its practitioner. This highlights a humbling truth. These ancient wonders were not just the product of brilliant individuals, but of sustained cultural ecosystems that could think in centuries. They required social stability, economic surplus, and a shared belief in a project grander than any single lifetime. The cathedral builders knew their names would be forgotten, their bones turned to dust long before the final spire was set. Yet they carved each gargoyle with care, laid each stone with precision for a future they would never see. This points to a powerful human factor beyond engineering, a collective faith in legacy. What other intangible forces, from religious fervor to civic pride, provided the will to mobilize thousands for decades? How did they maintain morale, resolve disputes, and house and feed such vast workforces in an age without modern logistics? The stones themselves are silent on these human dramas, but the fact that they stand at all is a testament to a forgotten mastery of organizing people, of turning a common vision into a mountain of coordinated effort. A city of 10,000 people appears in the desert, not to live but to build. This 31st dimension, the sociopolitical organization of mega-projects, reveals that the greatest engineering marvel was not in stone but in society itself. The physical monuments we admire are merely the final, solidified expression of a staggering human achievement, the mobilization and management of entire populations across generations. Consider the workforce that raised the Great Pyramid. Estimates suggest a core of skilled, permanent artisans and administrators, supported by rotating crews of laborers who may have numbered in the tens of thousands during peak seasons. This was not a chaotic mob. It was a meticulously organized, state-run operation on an industrial scale. The first challenge was creating life where none existed. At Giza, archaeologists have uncovered the remains of a purpose-built workers' settlement, complete with bakeries producing thousands of loaves, fish processing facilities, and barracks. This was a temporary metropolis with its own infrastructure, designed solely to sustain the human engine of construction. The supply chains that fed this city were feats of logistics. Grain was shipped from estates across Egypt, cattle were driven from the delta, and fresh water was likely brought by canal or a complex system of delivery. Every day required the reliable arrival of provisions for a small army, a system that demanded advanced bureaucratic record-keeping. Scribes would have been as essential as stonemasons, tracking shipments, ration distributions, and tool inventories on countless papyrus scrolls. This points to a sophisticated hierarchy. There would have been a chief architect, a master of the works, who held the grand vision. Beneath him, layers of overseers managed specific sectors: quarry, transport, construction, and provisioning. Foremen directed gangs of workers, each with a specific task and likely a team identity. Evidence from worker graffiti at Giza even suggests a sense of pride, with teams naming themselves after the pharaoh, like the Friends of Khufu gang. This reveals a crucial nuance about motivation. While some labor may have been a form of tax obligation or conscripted service, there is strong evidence for a system of compensated, organized work. Workers received wages in the form of bread, beer, oil, and cloth. Medical care was provided, as skeletons show set bones and evidence of surgery. This was not mere slavery. It was a national project that offered sustenance, community, and perhaps even social mobility for skilled individuals. How did they maintain morale over decades? Ritual, routine, and a shared transcendent purpose. The project was framed as a divine duty, a collective act that ensured cosmic order and the eternal glory of the king, and by extension, the entire kingdom. Seasonal work rotations allowed people to return to their farms, preventing burnout and integrating the project into the annual rhythm of life. The organizational power required for this was the true engine of early state formation. To build on such a scale, a central authority needed the ability to assess resources, collect taxes in kind, and command the labor of its citizens. The administrative templates created for pyramid building, the census data, the standardized measures, became the backbone of the Egyptian state itself. The physical engineering rested upon this invisible framework of human coordination, a testament to a forgotten mastery of people, time, and will. A king's command can echo for 5,000 years. This 32nd dimension, the role of ideology and leadership in driving innovation, asks us to look beyond the chisel and the lever to the very source of the will that set them in motion. The most sophisticated engineering technique is powerless without a reason to exist, and in the ancient world, that reason was often a fusion of the sacred and the political, a vision so compelling it could command the labor of generations. Consider the pharaoh, isolated in his palace, contemplating his legacy and his journey to the afterlife. His decision to build a pyramid was not a vanity project, it was a cosmological imperative. The structure was a machine for resurrection, a ramp to the stars, a permanent assertion of Maat, the divine order, against the chaos of the desert. This ideological engine was unstoppable. It justified the redirection of a nation's entire economic surplus, the creation of new administrative offices to manage the work, and the legal frameworks to conscript and care for a vast workforce. The project became the central organizing principle of the state itself. Innovations in record-keeping, like detailed census data and inventory systems, were likely refined to track the movement of stone, grain, and workers. Standardized weights and measures, essential for fair trade and taxation, found their most rigorous application in ensuring every stone block met its exact specification. The need to feed thousands in a remote location may have spurred advances in large-scale baking, brewing, and food preservation. The engineering challenge, in a very real sense, built the bureaucracy. Leadership provided the focal point for this immense energy. A single figure, whether an Egyptian pharaoh, a Roman emperor like Augustus ordering the construction of an empire-wide road network, or a Byzantine emperor like Justinian championing the Hagia Sophia, could unify a society's efforts toward a singular, awe-inspiring goal. Their authority cut through local disputes. Their vision provided a story that every laborer, from the quarryman to the water-bearer, could feel part of. This was not merely top-down coercion, though that element existed. It was also a profound social contract. In return for their labor, people received sustenance, community, and a share in something immortal. The pyramid or the cathedral rising on the horizon was a daily reminder of collective purpose, a symbol of identity that was literally carved into the landscape. It gave meaning to hardship and transformed routine toil into a sacred duty. The anonymous master builders, with their bottom-up ingenuity, were the essential partners in this grand vision. They took the ideological blueprint, the desire for a mountain of light or a doorway to heaven, and translated it into practical reality. Their innovations in ramps, levers, and mortar were the direct physical answers to the leaders' spiritual and political demands. This synergy is where true civilization-scale innovation was born. The dream of the palace demanded the genius of the workshop. The desire for eternity forced the invention of techniques that could defy time. What began as one individual's quest for immortality became, through the alchemy of shared effort, the enduring signature of an entire people. This interplay between the visionary and the artisan, between the dream of order and the grit of execution, suggests that our greatest structures are not just feats of engineering, but monuments to a shared story powerful enough to move mountains. The name of the master mason who first fitted the keystone of the Pantheon is lost to us forever. We speak of the Romans, the Egyptians, the Inca, as if these were monolithic minds. But every perfect joint, every precisely calculated ramp, every resilient batch of concrete began as a flash of insight in the mind of a single, anonymous individual standing on a dusty worksite. This is the quiet heart of the mystery, the collective genius of the unnamed. These lost techniques were not handed down by gods or a forgotten super-civilization. They were forged in the crucible of daily work, through the relentless, cumulative application of human observation, experimentation, and shared experience. Imagine the first worker who noticed that wet sand made a sledge slide more easily, or the mason who discovered that a specific volcanic ash, when mixed with lime, created a mortar that set harder underwater. These were not theoretical breakthroughs announced in a royal court. They were practical solutions born of necessity, whispered from one experienced hand to the next apprentice over a shared meal. This was a bottom-up intelligence, a slow cultural evolution of know-how. Each generation of builders stood on the shoulders of the last, adding their own tiny refinements, their local adaptations to different stones or climates, their clever tricks for moving a stubborn block. The master plan may have come from the architect, but the genius of execution lived in the calloused hands of the workforce. The true loss, then, is not merely a set of instructions. It is the dissolution of that living chain of practical wisdom. When a guild was broken by war, when a master died without a worthy apprentice, when a society's priorities shifted from monument building to survival, that fragile, unspoken knowledge could vanish in a generation. It was stored not in libraries but in muscle memory and shared routine. This perspective fills their achievements with a new, profound dignity. It was not magic. It was the focused intelligence of our own species, applied with patience across centuries. It asks us to look at a 2,000-year-old wall not with awe for some mysterious them, but with respect for the countless individual us who made it. And it forces a vital question for our own time. In an age of digital abstraction and disposable technology, how do we value and preserve the tacit knowledge of our own craftspeople, the welders, the woodworkers, the masons who still feel their way to perfection? Their hands hold a continuity with those ancient builders, a lineage of practical wisdom we dismiss at our peril. Recovering their mindset is not about rebuilding pyramids, but about rediscovering a way of thinking that solves problems in harmony with the material world. This brings our journey to its final and most urgent station. What can these echoes from the silent past teach us about building our own future? The concrete heals its own wounds, and the mountain dances with every tremor. These are not relics of a bygone age, but active lessons waiting to be read. The emerging field of archaeoengineering does not look at ancient sites as static ruins, but as dynamic textbooks of applied physics and environmental harmony. It asks a simple, revolutionary question. What if the most advanced building technology for a sustainable future is not in a laboratory of the future, but in the quarries and foundations of the distant past? Consider the principles at play. Roman concrete used a local volcanic pozzolana and seawater, ingredients that triggered a centuries-long chemical conversation to strengthen the material. It was a cradle-to-grave life cycle that improved with age. The Inca polygonal masonry required no manufactured mortar, just a profound understanding of stone and geometry, creating structures that maintain themselves through flex and friction. The Persian Qanat moved life-giving water across arid landscapes using nothing but gravity and a deep knowledge of hidden aquifers, a zero-energy system that sustained communities for millennia. These methods share a common philosophy. They are deeply place-based, using materials at hand. They are energy efficient, leveraging natural forces like gravity, compression, and thermal mass rather than fighting them. And they are built for permanence with a time horizon that stretches beyond generations. This stands in stark contrast to much of our modern built environment, which often relies on global supply chains, high embodied energy materials like Portland cement, and a design life that can be shockingly short. The study of these traditional knowledge systems is now fueling some of the most exciting frontiers of modern science. In the field of biomimicry, researchers are not just copying ancient forms, but decoding their underlying principles. Scientists are developing self-healing concretes inspired by the Roman recipe, using bacteria or crystalline compounds to automatically seal cracks. Architects are designing buildings with tuned mass dampers and flexible joints, directly echoing the seismic wisdom of pagodas and polygonal walls. The ancient practice of using specific plant extracts or mineral treatments to preserve wood and stone is informing the search for non-toxic, durable biocoatings. This is not a call to abandon steel and glass or to romanticize a past that had its own hardships. It is a pragmatic synthesis. It is about using our advanced tools of material science, computer modeling, and chemistry to understand why these ancient methods worked so well, and then to translate those principles into new, hybrid solutions. How do we create modern building materials that are not just strong, but actively resilient, that can adapt to stress like a living system? How do we design cities where water management mimics the gentle, distributive intelligence of a canal network, recharging aquifers instead of creating toxic runoff? The answers are emerging. Researchers are exploring geopolymer cements that, like Roman concrete, have a far lower carbon footprint than conventional types. Engineers are revisiting passive cooling and ventilation techniques from ancient desert architecture, which can drastically reduce a building's energy needs. The ultimate goal is a new paradigm, one that merges the deep time wisdom of the past with the transformative potential of the present. This conversation between millennia is perhaps the highest tribute we can pay to those forgotten masters. It moves their legacy from the realm of archaeological curiosity into the urgent work of building a resilient world. Their techniques were born from a dialogue with nature's limits. Our challenge now is to relearn that language not out of nostalgia, but out of necessity, weaving their enduring logic into the fabric of our future. Our journey through the labyrinth of lost ancient engineering reveals a landscape of human achievement far richer and more sophisticated than textbooks often allow. We have seen precision that baffles machines, logistics that defy scale, and a harmony with natural forces that we are still striving to relearn. These techniques are not merely historical curiosities. They are signposts pointing to peaks of knowledge that were reached, maintained, and then tragically lost. They remind us that progress is not always linear and that wisdom can be fragile. As we face our own global engineering challenges, let us look to the past not for mythical secrets, but for inspiration, for proof of what focused human ingenuity can accomplish. The stones still stand, waiting for us to listen to their stories. Share in the comments which of these forgotten techniques you find most astonishing, and subscribe to continue unraveling the great mysteries of our shared human past.